Hello, my name is Dr. A.J. Coomer, PhD. I am the smartest mathematician who has ever lived, and we're going to do Euclid's Elements, Book 1, Proposition 11. I have not even looked at it at all, so this will be a raw reaction. I have no idea if it's going to be a hard one or an easy one. What does red mean? Is red mean that it's a constructive argument? That seems to match the color scheme so far. What does red mean? Is there... Let me find red. Okay. The constructions are displayed. Okay, so that matches. Oh, that's interesting. He didn't draw a dependency tree, which is the normal way you draw dependencies. Anyway, let's go Proposition 11. To draw a straight line at right angles to a given straight line from a given point on it. Okay, I already know how to do this. Let me show you. And I bet I can predict what his construction is going to be. All right, so here's the idea. Let me tell you exactly how this is going to go. I've never looked at this before. In fact, I'm going to minimize this. And it's just to prove to you that I am the smartest mathematician of who ever lived. Not that I need to prove that. It's obvious. But so we're going to have a straight line. And I'm going to make it obviously not, off center. And we have a point on the line. Okay. What we're going to be doing, we're going to draw, we're going to take another point on the line, I bet. Okay. How are we going to do this? So we have a procedure for copying a compass, right? So what we're going to do is build an equilateral triangle with this in the middle. Okay. So let's think about our copying a compass procedure. So first thing, okay. Okay, we're going to copy this segment. Let me highlight it in a color. Okay, segment from C to D. Okay, and this segment, object properties. Okay, and then the original segment, I'm going to make it, thinner, okay, or less transparent, or less whatever. You know what I mean. Okay, and this, let's make this, let's take D, and let's also make this bigger. All right, so how do we copy the compass again? Oh, this is going to be a little bit annoying, right? Oh, no. No, here. Duh, we don't need to copy the compass. I'm a retard. I'm stupid. Let me show you what we need to do. I'm stupid. No, I'm not the smartest mathematician who's ever lived. No, we just take the other intersection over here. Okay? That's it. That's all we need. Okay, and now we build an equilateral triangle. Let's delete G. Okay. Now what we're going to do is we're going to build an equilateral triangle. Let me show you. With DE as the base. Okay. So this C, really, GeoGebra? Really? Okay. Okay, let me make this point C. Let's make it a green. Does that work? Okay, and then let's make this green as well. And let's just make everything really thick, and if we need to, we can play with opacity. Okay, this. And this is red. Okay. Okay, and so what we're going to do is we're going to use our procedure. Let's take D. Again, make it very thick, and let's make this blue. There we go. And let's take E, and we'll make it again. Let's make it not red. How about like a pink? How about a purple? There we go. And this C, this can go down. We don't need this to be. We need this to be very thin. Okay. There we go. No, thicker than that. 9. Okay. Let's see. So we're going to need to build an equilateral triangle here. So let's get to that. Let's do that. Okay, and then we'll just bisect this. That sound good? We don't even need to build the equilateral triangle, right? Okay, there we go. Done. Okay, but let us make the colors nice and pretty. And then we'll have to check and make sure this actually is Euclid's argument, because it's also likely that I made a mistake. Color. Style. Let's make this. Color. Go E. You know what we'll do? We'll bump up the opacity to like 75%, okay? That's what we're going to do. We're going to bump up the opacity. Okay, but we're going to make them dashed. There we go. Let's just make this red. Color, basic. There we go. All right, and then I'm going to want to hide all the labels because I don't like labels. I just realized that what women say when they say they don't like labels, what they mean is they don't like restrictive categories. They don't like the restrictions imposed by the cultural system, because it's always like weird girls who say that, and it's that they don't like. It's like culturally rebellious girls. And they don't like the, because culture is the system of categories, right? And what they don't like is the rigidity imposed by the system of categories. Anyway, here we go. So we can do this. We can move these around. And there we go. We've constructed a straight line at a right angle. Why is this opacity all the way? How about that? Oh, because it doesn't have the gray behind it. That's the issue. Anyway. So here we go. This is the construction, I bet. I don't know for sure. This looks like a kind of a cool logo. This looks like a logo for some weird church that you would see in like Denmark, right? All right, let's look at Euclid's proof. All right. Let AB be a given straight line, and let C the given point on it. It is required to draw a straight line at right angles to this. Oh, he doesn't say. Ooh, right angles. That's interesting. Okay, I didn't notice that caveat. I mean, that's the construction, but how do you do the argument? Okay, so you'd have to argue. Ooh, how do you argue that these are right angles? That's going to be interesting. Okay, let AB be the given straight line, C be the given point on it. So AB, so our two little endpoints, and then our green point right here. It is required to draw. Let me give this a different color. It's required to draw a blue line that is perpendicular to the gray line. And actually this, do we need this green circle at all? Let's, because this isn't really important. Let's make it, there we go. That's too light, but I think dashed and dotted are better than all right, there we go. Oh, you know what I was upset with is this. I don't think we need that. Right. Yeah, we don't need that. Okay. So take an arbitrary point D on AC, make CE equal to AD to CD, I guess what we just did. Construct the equilateral triangle FDE on DE and join CF. Okay, that's what we did. I say that the straight line CF has been drawn at right angles to the given straight line AB from C, the given point on it. Since CD equals CE and CF is common, therefore the two sides CD and CF equal the two sides CE and CF respectively, and the base DF equals the base EF. Okay, so CD equals CE, CF is common, therefore CD and CF equal the two sides CE and CF respectively, and the base DF, right, because of the straight line, because of the equilateral triangle construction. So that's part of the argument, but not part of the construction. The base, this is an interesting idea that in order to argue something, in order to argue a fact, you need more data than you need to construct the whatever. The base DF equals the base EF. Therefore, the angle DCF equals the angle ECF, and they are adjacent angles. Okay, so when a straight line standing on a straight line makes the adjacent angles equal to one another, each of the equal angles is right. Therefore, each of the angles... So I'm going to pull up these definitions over here. When a straight line standing on a straight line, what does that mean? Makes the adjacent angles equal to one another. Each of the equal angles is right. Therefore, each of the angles DCF and FCE is right. Therefore, the straight line CF has been drawn at right angles to the given straight line AB. The straight line CF has been drawn at right angles to AB. Okay, so this argument about why these are right angles, that's interesting to me. So let's look at this. When a straight line standing on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called a perpendicular. Okay, so almost by definition, because these two angles are equal, and what it's saying is that if two angles add up, if an angle plus itself equals a straight line, then it's a right angle. Okay, that's what definition 10 means. Okay. All right, let's read the guide. This and the next proposition both construct a perpendicular to a line through a given point. The difference is that the given point lies on the line in this proposition but doesn't in the next. The actual construction here is the same. Look, it's exactly the same as what I did. I bet even the if we turned on the labels, it would be exactly the same. Let's see. It's exactly the same construction. See, I am as smart as Euclid. Although I'm smarter than him because he was a mathematician and I'm the smartest who has ever lived. Anyway. Yeah, this construction, okay. This construction is used in propositions 1.13, 1.46, 1.48, and numerous propositions in books. Let's see about my Roman numerals. 2, 3, 6, 6, 11, 12, and 13. All right. See you in the next video. Goodbye.